Welcome back to topic 46 for Algebra 2, Graphing Radical Functions. In part 2, we're going to learn how to graph transformations of radical functions, as well as how to identify the domain without graphing, so just from an equation. For transformations, it's really helpful to think of a radical function in vertex form. Here we have y equals plus or minus a times the nth root of plus or minus x minus h plus k. Looking at all these different variables, keep in mind from our parent functions topic that our vertex is at h, comma k. So these two values right here. Now if we go through this entire vertex form, let's identify what each variable means. We're used to seeing our function being positive. However, if we have a negative here, that means that there is a reflection across the x-axis. The A out front represents a vertical stretch, or compression. Depending if it's a whole number or a fraction. Now, moving on to the radicand, what's underneath the radical, we're used to also seeing it positive. However, if it is negative, this tells us that there is a reflection across the y-axis. Now notice here before I move forward, we have x minus h. This is going to come in handy when we look at some examples. So remember that for the vertex form, it's x minus h. This h represents a horizontal shift. And the k represents a vertical shift. Okay, now let's apply what we know to some examples. Our first example, we have h of x equals the square root of x plus 2 minus 2. Let's first identify what the vertex would be. Well, remember, for our radicand, it's x minus h. So this is really the same thing as the square root of x minus a negative 2 minus 2. Two negatives, when multiplied together, make a positive, which is why we see x plus 2. But our h value is actually negative 2. So our vertex here is going to be at negative 2, negative 2. Now, because there are no other transformations, we can use our parent function of the square root function in order to graph the rest of this. You can also plug this into a table, but we know that this is the same thing as shifting to the left 2 units as well as down 2 units. And there's our function. Now looking at our graph, we can also identify the domain and range. Domain is all the smallest possible x values, and the range deals with your y values. The smallest possible x value that we see is negative 2. Since we have a point here, that's why we're using a bracket. And it gets bigger and bigger until it goes towards infinity. Range, the smallest possible y value that we see, is also negative 2. And if we were to zoom out on our graph, we would see it would get bigger and bigger, also approaching infinity. Since infinity is not finite, it's indefinite, that's why we have parentheses here. Moving on to our next example, g of x equals the cube root of x plus 2 plus 3. Cube root of x plus 2, if we think back to, remember it's x minus h, so this is really the cube root of x minus a negative 2 plus 3 my vertex is going to be at -2, 3. So let's plot that. Now again, since there are no other transformations in this function, we can use our parent function of the cube root in order to graph it. And again, you can also plug it into a table if that's helpful for you as well. Looking at our graph, the x values go from -infinity to +infinity, and same with the y values, or a range. Let's go on to the next example. F of x equals the square root of 4x plus 16 plus 7. Now right off the bat, this doesn't look like it's truly in vertex form. We can actually simplify this. So let's first rewrite it. The square root of 4x plus 16 plus 7. Now if we want to focus on the radicand, the values that are underneath the radical, we have 4x plus 16. Can we simplify that any further? Well, we can factor out of 4 to get the square root of 4 times x plus 4 plus 7. Now thinking back to simplifying our radicals, the square root of 4 times x plus 4 plus 7 is the same thing as the square root of 4 times the square root of x plus 4 plus 7. So we can simplify the square root of 4, and it gives us 2 times the square root of x plus 4 plus 7. Here it's a little bit easier to identify what our vertex is now. Our vertex is at -4, 7. Now also note here how we have a vertical stretch of 2. So our graph is going to appear a little bit steeper, and we can also plug this into a table of values if we want to get those specific points there. Here, unfortunately, it is going to go off the graph a little bit. Our domain, the smallest possible x value that we have, is -4. Again, we have a bracket because that is a point on our graph. And goes to +infinity, and our range is from +7 to +infinity. Moving on to our last transformation, here we have q of x equals -3 times the cube root of x. Now here, it's not as easy to identify the vertex right off the bat because we don't see any h or k values. Not yet, that is. This is really x minus 0 plus 0. So our vertex is actually at the origin. Now here we have this negative sign. So this tells us that we are reflecting across the x-axis from our parent function. And this 3 is telling us that we have a vertical stretch of 3. So we're going to multiply those initial values by 3 after. Now I'm going to take a quick look at our parent function in order to kind of get a grasp on what this graph will look like, keeping in mind those transformations. So our parent function, remember, kind of looks like a stretched out S in a way. But if we were reflecting across the x-axis, we will get a graph that will flip and look a little bit closer to this. So this is what our graph will look like flipped over the x-axis. But we also have it multiplied by a factor of 3. So, since it's multiplied by this factor of 3, and we know our graph is flipped over the x-axis, instead of having over 1, up 1, and down 1 to the left 1, we're instead going to have over to the right 1, down 3, over to the left 1, up 3. And instead of being over to the right 8, up 2, since we're multiplying by that factor of 6, we're going to the right 8 and down 6. Over to the left 8 and up 6. And here's what our transformation will look like. Here the domain goes from negative infinity to positive infinity, and the range also goes from negative infinity to positive infinity. So again, here we can see that vertical stretch of 3, as well as the reflection across the x-axis and how that changes our graph from the original parent function of the cube root of x. Now we can also identify our domain without actually graphing, just looking at the equation. Keep in mind that we do have some restrictions on the domain. What we learned about in our rational functions unit is we can't divide by 0. Otherwise, it will give us a value that's undefined. Now, what we're specifically going to focus on in this unit on radical functions is for a domain of a real number system, so we're not dealing with imaginary values, the square root of a negative number does not exist. So for example, in other words, to summarize, our domain restrictions, we have the set of all real numbers where x is greater than or equal to 0. So the value in our radical can either be 0 or bigger or positive. We can do that because we know we can't take the square root of a negative number, so we're going to look specifically in our radicand here. So x minus 5 is greater than or equal to 0. Now we can solve for x. Add 5 to both sides, and we get x is greater than or equal to 5. Now if we want to write this in interval notation for our domain, this leaves us with, since 5 is the smallest possible value, if we think back to our inequalities, it's pointing to the smallest value, then we'll go until it gets bigger and bigger, closer to infinity. Now because we have an or equal to with our inequality, that's why we can use our bracket. Moving on to the next example, we have y equals the square root of x plus 3. So here x plus 3 must be 0 or larger. Solve for x. So x must be greater than or equal to negative 3. In interval notation, this is from negative 3 to positive infinity. Two more examples. F of x equals the square root of 2x plus 3. So 2x plus 3 must be 0 or larger. Solve for x. Divide by 2. So x is greater than or equal to negative 3 halves. In interval notation, we have from negative 3 halves to positive infinity. Last but not least, here we have y equals x minus 4 to the 1/2. Remember, this is a rational exponent. And it is equivalent to a square root. So this is the same thing as y equals the square root of x minus 4. Again, we're going to focus on that radicand. set that equal to 0 or larger. So x minus 4 is greater than or equal to 0. Add 4 to both sides. X is greater than or equal to 4. So our domain is from 4 to positive infinity. And that was part 2 of topic 46 for Algebra 2 on graphing radical functions. Thank you for watching.